All right, so we know that if we have our cloud, we got to have some kind of a thing for it to form on, right? Can't get a cloud unless we got some kind of a condensation nuclei. A speck of dust, a piece of dirt, a piece of smoke, ash, whatever, something. So now we've got our cloud. So we know our different cloud types. We'll run through those real quick again, just so you kind of get an idea of what we're looking at. All right, so we have our cirrus clouds, right? Our high little wispy guys. We have our middle clouds. That's our alto clouds, our alto stratus clouds, our alto cumulus clouds, which is more like an alto stratus what we're seeing today. And then of course we've got our low clouds, our stratus deck. That kind of looks like outside, doesn't it? Yeah. There you go. And then we have our vertical development clouds, our cumulus clouds, so our little puffy popcorns. When it starts to get a little bigger, they congest together. And then our cumulonimbus clouds. And remember, if we have that word nimbus, it means what? Right, it's a rain cloud, exactly. Okay, so we got all that. So now we got to figure out how rain works, or how precipitation works. So precipitation is basically water that falls from the sky. And it can fall in the form of either a liquid or a solid. Obviously, if it is a solid, it is either ice or snow. Or if it is a liquid, it is rain. Okay? So how do we know, or how do we figure out how things fall out of the sky? Well, one of the most important concepts that we use to this is the idea of what's called terminal velocity. Okay? Now, terminal velocity is the speed of, or the constant speed, I should say, of a substance or a particle falling through fluids such as like water or air. Okay? It's regulated by gravity and the resistance of the air itself. So gravity is going to pull it down. The air resistance, which is sort of the amount of push or pull that substance has on this particle, are moving in opposite directions. Obviously, gravity usually wins out because it's the stronger of the two forces. Okay? So when these forces balance, it attains sort of a constant speed as it's falling from the cloud. It goes to the idea of Newton's first law of motion. Object in constant straight line motion, or at rest, remains that way unless acted upon by an unbalanced force, right? Meaning that if I have a ball sitting on a table, that ball will continue to sit on the table until some force moves it. All right? So how do we get this precipitation to fall? Well, first we're going to figure out how big is it. And the important factor, or a important factor I should say of this, is what's called its terminal velocity. Sort of at what speed does it actually fall through the sky? Okay? Now, as you might expect, the larger this particle or substance is, the faster it's going to fall, right? Makes sense. So something like gas molecules, ions, smoke to even some degree, a little bit of haze. Notice that the terminal velocity is not very strong, meaning it falls however many centimeters per second. Because it's very light, it's not very dense, it can remain stuck up against that air resistance. Now, the bigger something gets, cloud droplets, drizzle, raindrops, hail, obviously as the size of something increases, the terminal velocity is going to increase as well. People should be way out here. So that's why if we've got cloud droplets, notice that their terminal velocity, or the rate at which they'll fall through a cloud, are less than an actual rain droplet, right? So the way to think about this is that everything kind of builds on itself. So you have something that starts off super small, and through a couple of different processes, which we're going to learn about, they get bigger and bigger and bigger, to the point where that air resistance can't sustain the weight or the density of that substance. And so as soon as that substance gets too strong, terminal velocity takes over. And gravity sort of does its thing. And basically the bottom line here is that the reason why tiny water droplets and ice crystals, a la clouds, don't fall as soon as they form in the sky is because they're not large enough to do that. A student asked years ago, I thought it was a great question. They said, well, if it's a water droplet, if that's what clouds are made of, then why don't clouds just fall from the sky as soon as they form? I thought it was a really good question. That's why. Because the water vapor that's up there, the cloud nuclei, the cloud droplets that make up that cloud are so tiny that gravity doesn't really have an overarching effect on them. They have to get big enough so that it can take over. And that's where you get your raindrops, your hail, your drizzle, snow, things like that. So, two different ways that we can get things to kind of grow in a cloud. There's the idea of what's called collision coalescence and Bergeron process. So the collision coalescence is basically just what it sounds. It's droplets that collide, they merge together, they get bigger, and as they get bigger and bigger and bigger, they get to a point where they can't be held up by that cloud anymore, and they start to fall. Okay? Now here's the interesting thing. Just like, have you ever heard the thought or the term that no two snowflakes are the same? They're very different? Right. Well, water droplets are the same way. Even though when we draw them out, or if you see them in pictures, or if they're on a video or whatnot, they always look the same. That's just to try to create uniformity. They're actually very different. And that's a really important part and a really important point in a cloud, is that they have to have a mixture of droplet sizes, okay? Because obviously if you've got all small, then the chances of them sort of colliding or smashing into each other are going to be less than if you've got like one big one and a bunch of small ones that all kind of roll onto it. Has anybody played that silly game on your phone? It's called Holio. Nobody? Good. Thank goodness. Anyway, it's the silly game where you literally are just a hole and you go around and just eat things up, like buildings, cars, other holes. Yeah. It apparently took over like 6 months ago. It's a hot game, but it's very silly, but it's the same concept. Is that if if a water droplet hits another droplet, they merge together, the size or the volume of that new droplet is going to be bigger because you put the two together. Makes sense. Okay, so eventually these droplets become large enough, the terminal velocity overcomes the updraft, and precipitation starts to fall. Bam, there we go. So collision efficiency increases with the size of a larger droplet, which makes sense, right? If it's kind of like the Pac-Man game. If you've got a raindrop that's bigger than the others, then the chances of that smashing into other ones as they're rolling around in the cloud are going to be a lot bigger, or a lot better, I should say, because it's a bigger raindrop. So it makes that whole process much more efficient. So this is basically a good descriptor of what it looks like. So you have all of these little water droplets in the cloud. And you have a little raindrop that's starting to form. And so as it goes through the cloud, as it falls through, notice that it sort of creates a path or a lane by basically cannibalizing all the other droplets around it. And in doing so, it gets bigger and bigger as it continues to fall. And as it gets bigger and bigger, it gets to the point where its volume, its size, its weight is too big for the cloud to hold it anymore, and it starts to fall as precipitation. So that's the overall essence of how this works. All right, so that's a warm cloud precipitation. So just sort of your basic precip here. All right. So now, in a cold cloud process, it's something called I call it find a sense fine. We'll just call it the Bergeron process, just keep it easy. So these are cold clouds. So we're talking about middle, high latitude clouds. So our stratus clouds, or excuse me, our alto clouds, I should say, not stratus, it's the low side. So our alto clouds, alto cumulus, alto stratus clouds, and all of our high clouds, which are the cirrus clouds. Okay? So the cirrus clouds, this is where the temperature is less than 0 degrees centigrade. So basically a cloud that's freezing. So it's got full of ice crystals. So the concept, or the collision process, the forming process, the precipitation process is going to be a little different because we're not dealing with necessarily a water-based particle. This sometimes can be ice. So it's going to act differently in the sky. So most of the precipitation that we have in these middle and high latitude clouds comes in the form of either supercooled water or ice crystals, which is why cirrus clouds are real thin and wispy, and sometimes you can get little rainbows off of them if you look in the sky because it's all ice crystals. So you can refract the light. So sub-freezing temperatures, water molecules readily vaporize from a liquid to an ice surface because the molecules have stronger bonds in the solid phase, which makes sense. Okay? So the vapor pressure saturated for water droplets is supersaturated for ice crystals. What do I mean by that? Meaning that the water vapor that's surrounding other ice crystals can grow and turn into more ice, so it doesn't necessarily have to go through that liquid phase. So it can go from sort of a water vapor, almost like a gaseous phase, straight to a solid phase. So it doesn't necessarily follow the same rules that the other precip does in clouds. Okay? However, the interesting thing is that as these ice crystals start to fall, okay, as they kind of move around a cloud, they actually follow the same process, right? Because remember, the number one thing that rules in any weather situation, or in any situation in nature, is gravity. Gravity is the overwhelming force, okay? So the same story is that as the ice crystals grow larger, they fall faster and collide with the droplets and other ice crystals. So you've got all of our little super cooled cloud droplets here, pop, 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 pop. A few ice crystals, and then as those fall through the sky, or fall through the cloud I should say, they bond or they stick with other smaller cloud droplets. And so as those get bigger and bigger, they eventually get to a point where they are large enough that the cloud cannot sustain or hold them up anymore, and it starts to fall as precipitation. So the overall product is the same. That these collide, coalesce with each other, and as they do, they get bigger and bigger. And as they get bigger and bigger, they start to fall. So that's the process of how we get precipitation started as it moves its way out of the cloud. Okay. So not all the time when either raindrops, snow falls out of a cloud does it actually reach the ground. Sometimes it vaporizes before it does. Okay. So once these ice crystals of the rain leave the base of the cloud and they enter into an unsaturated air mass, basically they come from a cloud which is fully saturated, so they've got all this moisture. They get out of that cloud and they get a little further down and they get into maybe a drier environment. What can happen sometimes is that the higher this cloud base, the more space that has to go through to make it down to the ground, right? And so what can happen in particular is that a lot of times these droplets, water droplets, ice crystals, whatever they are, start to fall, and as they do, they begin to vaporize, meaning they just dry out.
and evaporate. Okay? But we don't see that much here. Once stuff falls from the sky, it pretty much makes it to the ground, right? So the downpours we get all the time. But this is very common out in, let's say, the desert Southwest. What you'll see is you might see a big thunderstorm cloud, and you'll see these like streaks of things that are falling out of that cloud, right? But the problem with that is that all of this that's falling out of the cloud doesn't make it to the ground. And so it falls and evaporates, and when it does that, it's called virga. So it creates these streaks of water, these ice crystals that are falling, but they vaporize before it reaches the Earth's surface. Now here's the interesting thing about virga, is that evaporation is a cooling process. Okay? I'll explain how that works. So if I have a cloud droplet, right? Say I got a little water droplet. We got like right there. There. Okay? So these are all falling through the cloud. Once they get into this environment where they get into a drier air mass, they're going to start to evaporate. What happens, in order to evaporate, in order to make this water turn into a vapor, which is basically what we're trying to do, we have to do what to it? If I'm going to try to dry that out, do I have to take heat away from it, or do I have to add heat to it? I'm going to try to dry it out. Yeah, you're going to take heat away from it, right? So you're trying to take heat away. So what I have to do is I have to pump all of this energy into this cloud, or into this droplet, to try to be able to dry it out and take the heat away. So if I'm doing that, if I'm taking energy away from the surrounding environment and I'm putting it in here so I can dry it out and take it away, what's happening to the energy that's surrounding that droplet? Is it going up or is it going down? I'm taking it away from, it's going down, right? Because I'm taking it away from the environment and I'm putting it into that droplet. Okay, well if I take energy, and we know that, right, in weather terms, we can equate energy with heat, right? So if I'm taking heat away from the environment here and I'm putting it into this droplet, if I do this 300 million times, because there's all these little tiny droplets out here, what I'm actually doing with this virga situation is I'm cooling this air mass. So the air actually starts to cool around these droplets. And as it cools around these droplets, it can allow the entire cloud base to drop. So what can happen with virga sometimes is that it starts off by not hitting the ground because it's too dry. But as we're taking heat away from the environment here and we're creating more moisture, you can actually get to the point where virga can make it down to the ground because it saturates the whole column as it works its way down to the surface. So most of the time, virga doesn't make it, just kind of evaporates. But if you get the extreme scenarios where you can really get it cranking, it can make it all the way down to the ground. But that happens a lot in the desert, out in the Southwest. You get it a lot up in the Northwest as well, where it'll get close, but it doesn't necessarily make it to the ground. Lightning does, but the rain doesn't. All right. Okay, so let's talk about our little preset forms here. So the liquid comes in two forms, rain and drizzle. And you say, well, what's the difference? I'm glad you asked that question. The biggest difference that we notice between these two is diameter. Okay? So rain is bigger and drizzle is smaller. Now you don't need to memorize like, oh, what's the diameter of that? No, just know that rain's the bigger of the two, drizzle is smaller. So one can become the other. If you get enough drizzle and you keep pumping moisture into that cloud or that structure in the cloud, it can actually create raindrops. Now drizzle mostly originates in stratus clouds and has limited growth because of this coalition coalescence. Okay? So that's why yesterday, today, tomorrow, with this cloud deck we have out here, our rain chances are going to be pretty light. Like there won't be much that falls, but most that does will all look like this drizzle that sort of falls through the sky. And then the rain comes out as these sort of flattened little spheres. So it's not your typical raindrop. That's something that the artists have created over the years. It's fairly unstable at big diameters and breaks apart. Okay? So those are our two liquid forms. Now, frozen forms get a little more interesting. Because our liquid forms, there's really only two different ways that you can make a liquid form of precipitation look. It's either going to be a raindrop or drizzle. Super, super light. Frozen forms of precipitation can be all kinds of different shapes. And one of the reasons why that is because it all based on what temperature and at what height it grows or it forms. So the colder you are, the higher you are in the cloud, the different type of a frozen precip you're going to see. So if you look on here, you notice that we've got pretty much everything that looks like a normal snowflake, right? That one looks like one. That's sort of typically what we think of when we see a snowflake. This dendrites, more dendrites down here. But the crazy part is that snow can actually take all kinds of different forms. Now, once it falls and it all kind of like collects in a clump, it pretty much looks the same, right? It's just, oh, that's snow. But if you were to take it under a microscope and you were to look at it in particular, you would notice that it actually has very different forms based on where it forms in the cloud. So when you get close to 32 degrees, a lot of times you'll get these little dendrites. You might get these little flat platelets. As you go up in the cloud and as you increase in height, which obviously is going to get colder as you go up into the cloud, you'll change the form. And what can happen sometimes is as you get to, let's say, about 10 degrees below, so probably low 20s Fahrenheit, you're getting colder. And so as you're getting colder, there's less water vapor to deal with, right? So your snow growth isn't going to be really big. It may be very small. So you might get these little plates or get these little columns. What's really interesting is when you get into really cold environments and you get into fairly dry environments, but there's still enough water vapor for it to actually form some kind of ice crystal, you'll get these little needles. I've seen these once. They're really crazy looking. It's like pickup sticks. But they're these little frozen pickup sticks that are just thrown all over. Happens a lot in like Montana, Idaho. Just want to find a picture of them. They're really crazy looking. Now obviously that wouldn't happen here, right? Remember last winter when we had the snow? Which I know because I was out of town, but I heard everybody losing their minds here. But when we had the snow, it was what? It was really thick stuff, right? These big flakes that was falling down. Obviously most of it melted by the time it did. But you get the idea, is that the snow growth zone that we were seeing was right around in here. So between about 10 and 20 below Celsius. Let's see if I can find a picture of it. Yeah, so that's kind of what it looks like. So it's these little tiny, there's ice crystals. And they just form whenever they hit. They just stick to stuff. So it's these little tiny crystals. So it's still cold enough that it can sustain a frozen environment, but there's not a lot of moisture with that, because obviously it isn't growing when it's in the cloud. It's these little tiny little needles. So this is what, so that if you look at them close up, here's what some of the dendrites look like. Right? Crazy, huh? Now notice.
Actual snowflakes
Yeah.
under a microscope?
Yep. In the wild, yeah. So they come in all these different forms, but if you notice, every single one has a core, right? Now go back to chemistry, and remember that if you're putting substances together, if you're putting molecules together, what do they, remember what we did with H2O yesterday, what do you have to have? You gotta have a core, right? You gotta have some kind of core. So the same thing exists when we talk about snow. Because it's an ice form, it's a crystalline form, it's gonna behave and act like a solid would when you put different molecules together. They're all gonna sort of form off of whatever base there is. So those are dendrites, that's sort of our most common form, what we normally see.
So if you're near the ocean, does snow look different because there's like more salt in the air, or just
Yeah, not necessarily more salt, there's more moisture in the air.
moisture? So
Yeah.
it's strictly moisture, it's not really elements?
Not necessarily. Mm.
Oh.
Yeah. No, you could. I mean, if you have, the elements will come into play because it'll just create more nuclei for a snowflake or a droplet to form on. So if you've got, if you've got a lot of sea spray in the air, you know.
It'd be less like.
Not necessarily. It could be more, theoretically, it could be more because you've got more stuff for that,
Okay.
for the water vapor to form onto.
Okay.
Then they can form onto all of the salt crystals. But yeah, you probably would get, in that scenario, you would just get more precip availability to fall because your moisture content's a little higher if you're near the ocean. But the other flip side to that is that sometimes the ocean can wreck the snowfall
Right.
because it's too warm.
Right. I guess there is that.
Yeah.
Oh.
So that's why you say, okay, well, you know, it's super cold up in the northwest, but it doesn't really snow that much. And partly
Moist,
because,
yeah.
it's just there's a lot of moisture, but it's too warm. You need to be able to pump in that cold Canadian air, and a lot of times that's all headed over into the Central Plains, and the Northwest basically just sits in a mild environment, so to speak. So this is what the pins and needles look like. Now notice they're pretty thin. And that's just because there's not a lot of moisture for them to work with. It's a pretty cold environment. Here's kind of what we think of when we think of our snowflake, right? Little dendrites. These are crazy. So these little flat platelets. So again, this would be a more drier environment. You can see something like that. And here's an interesting one. So what you can get sometimes with snow is you can create sort of a hybrid of like snow and ice, and it's called grapple. Looks like that. So grapple is basically just soft ice. It's sort of like little tiny bits of snow that are trying to form and freeze. Well, frozen anyway, but they're trying to form into ice. And they don't necessarily do that. You ever had those Dippin' Dots? You've seen those things? That's kind of what grapple's like, right? Because the Dippin' Dots, you know, when you first put it in your mouth, you're like, oh, it's frozen, and then it just melts real quick, right? So grapple does the same thing. That's why I call it soft ice. So if we've had it here, actually. I think we had, not last year, maybe 2 years ago, we actually had some grapple falling, and everybody's freaking out. So it just forms, and it's a soft ice, so as soon as it hits something, it usually melts like that. But it's out there. So snow can take all kinds of different forms. All right. Now what's interesting sometimes is that based on what falls from the cloud into what environment will prove or change as to what it is. Huh? What do I mean by that? Well, meaning that the environment below the cloud base is going to be crucial about what form of precipitation actually makes it to the ground. So for example, if, let's say this is, we've got a really cold air mass right here, and we've got a little bit of warmer air okay? So we got a really cold air mass there. We got a little bit of warmer air that's trying to nose its way in. That's going to change the type of precipitation that we're looking at. Okay? So if our cloud is here, now everything, and here's the trick to this too, which is really kind of interesting. Everything that falls from a cloud originally starts off as snow or ice. And then it warms as it moves into some of the air mass below. So it's all going to start as snow or frozen ice product in the cloud, and then as it starts to fall, it gets into a bit of a warmer environment. Some of it melts, some of it refreezes, just depends. So if it's an entirely cold column of air, so from the cloud base all the way to the ground is a very cold frozen environment, it's all going to fall as snow. Okay? So let's say here comes our warm air trying to nose its way in. Gets middle part of that column of air below the cloud before we get to the ground. So as that snow or that ice falls, it runs into some warmer air. It starts to melt, but then goes back into a colder air scenario again. So it can fall as the form of sleet. So sleet is just kind of like little ice pellets. So started off frozen, melted a bit, gets kind of turned into these Frankenstein-looking little pellets, and then falls as ice. Okay? And obviously, if most of that column is warm, all that snow or that ice is going to melt and turn into water, rain, by the time it hits the ground. Now, the most dangerous of all of these is the freezing rain. Okay? Freezing rain is a very specific scenario. You got a frozen column just below the cloud, and then it runs into a huge warm pocket. So almost its entire travel from the bottom of the cloud all the way to the ground is warm, so basically above freezing. So that ice melts, turns into water. But then right at the surface, it gets below freezing again. So it freezes over, okay? Anybody ever remember that stuff they used to put on ice cream called Magic Shell?
Oh, yeah, I remember.
Right? Yeah. Have you ever seen it? I think they still have it in the store. If they do, you should get it. It'll blow your mind. It's called Magic Shell. It's crazy. Huh?
They're too young.
Yeah, could potentially be. But it's really good.
Wanted hard.
Yeah.
Like instantly. It was so
Yeah.
fun.
So what it is, if you're not familiar, it's just like chocolate sauce or strawberry, whatever. And you would put it on your ice cream, and as soon as it would touch your ice cream, it would form into a solid. Yeah. 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 It's crazy. So, but that's kind of the same scenario for how freezing rain works. So imagine if this table here was a block of ice, okay? And I took water from a medicine dropper, okay? Little water droplets. And I went all over this table. What would happen to that water as it started to interact with the ice? What would it do? It would freeze, right? So that's why freezing rain is a very dangerous scenario. Because what you're doing is you're taking water, rain, and you're basically putting it on a frozen surface, right? That's why, what was it last year? When was it? I don't remember when. But we had a real good freeze, and it rained, and all of the bridges and the overpasses on 59 were frozen. The road wasn't frozen, but the bridges work because obviously there's no space underneath it, right? So it's just super cold. So the chief weather guy, Frank, and I sat there that evening, and we literally watched people from our tower camera, the Channel 2, that shoots over towards the Southwest Freeway. We watched people skid out as soon as they would hit the bridge. We're like, here comes, he's going too fast. Go, yep, there we go. And they would go up on the bridge, and they go, shh, and just and get stuck. And somebody else go up and shh, and they bang into that person. It was like watching a movie. It was crazy, you know? But that's a perfect scenario where the air was warm enough that it was sustaining rain, but those bridges were frozen. So as soon as that water hits the ground, it freezes. Yeah, freezing rain is no joke. It is very, very, very dangerous. So that's the 4 different forms of precipitation that we can use, all based on what kind of air mass is this falling in. All right. Now another really cool form of precip is called hail. Hail is basically just sort of a ball or a big lump of ice. Okay? So it's characterized by concentric internal layering. What does that mean? Basically it's an onion. Think of it as sort of like a big ice ball onion. So it's all of these different little layers of this ice that have formed around some kind of a core or a nucleus, right? And so as it goes through a cloud, it gets bigger and bigger and bigger and bigger. Now it's formed generally in thunderstorms, big thunderstorms at that, by the way, with big updrafts, an abundant supply of super cold water droplets, and basically a huge cloud, vertical cloud development. Okay? So what happens is in the updraft, in the part where the thunderstorm is kind of sucking in all of this air, it's cooling, it's condensing, it's creating water droplets. Those water droplets freeze, and as they freeze, they start to get too heavy, so they start to fall. As they fall through the cloud, they may melt a little bit, and they pick up other water droplets, so they get bigger and bigger. But because these thunderstorms have this big updraft, which is basically, think of it as like a big vacuum cleaner, these hailstones can melt some, fall through the cloud, and then get shot back up in the cloud where they refreeze. So hail is sort of a combination of a freezing and melting process that happens over and over and over and over until it gets big enough that the updraft can't support it and it starts to fall. So around here, the type of hail that we get is generally very small. Pea size, penny, maybe up to quarter size hail. But the trick to hail is that you've got to have a really cold environment. So your thunderstorm that's developing that hail has to be super cold up top. Well, obviously that's a bit of a problem down here, right? Because it's rarely ever cold. And so we just can't sustain hail. But if you get up into the plains, Nebraska, Iowa, the Dakotas, Oklahoma, you can really get some hail cranking. All right? I'm going to show you the size of some of these. So hail can go any size from a pea to like a grapefruit. Yeah. So pea-size hail is going to be more of an annoyance. Grapefruit-size hail will kill you, right? Because think about how fast this stuff's coming out of, we talked about terminal velocity, right? Some of the hailstones that they've clocked in some of these thunderstorms, when the storm chasers are out there, they've clocked them at like 120 miles an hour. So imagine someone taking like a ball of ice that's like a baseball and throwing it at your head at 120 miles an hour. That would hurt.
Did you see that mom that protected her baby?
Yeah, it was all pelted all over her bed.
So how big do you think those were?
That was probably baseball-sized hail, I would say.
And does it usually last for, is it short intervals?
It's pretty short, yeah. Because it's fairly short. It may be 30 seconds, it may be 2 minutes, whatever it is. But I mean, it's just absolutely Yeah, it's like an unlimited supply of baseballs coming at you. They're all coming at 100 miles an hour. So let's see if I can find some good. Let's find some good hail video here. Shall we? Yeah, it's there. All right. So this is kind of what it can do sometimes. All right, that would suck, wouldn't it? What they call the old dimple darlings. So there's one. Yeah, this is the one you were talking about. That's the story. So that's what was hitting her. That's a baseball. That's what was pelting her in the back as she was trying to protect her kid. Pretty wild, huh? So it can come in all kinds of different forms. You know, tennis ball size hail. That's not good. You know, then it comes smaller. Here's golf ball size hail. Now what's interesting about this one in particular is if you notice this, it's not like this smooth little shaved ice, is it? It's a lot more jagged. So the reason why that is because this probably didn't have a lot of other hailstones around it. Meaning that as it falls, it starts to melt. And obviously it's not going to melt in a perfect circle. It, oblong melts. And then as it goes back up into the cloud, it's still kind of mushy ice. And so let's say more ice attaches to it. And then it refreezes. Well, now it's kind of creating this weird looking shape. So the reason why hailstones sometimes look all smooth like this is because they've been up in the cloud long enough that they're kind of getting smashed up a bit. And so as they hit other hailstones, it sort of carves them out and tears off some of the rough edges around it there. But yeah, hail is no joke. That is not something you want to mess with. You know, there's what, 5-inch hail. So from South Dakota, right? So all these spots we're talking about, Colorado, South Dakota, these are all pretty cold weather spots where you can get. And most times when you get these big hailstorms too, it's generally in the spring because you'll get like a really warm air mass that moves in, so you're pumping all this moisture in, but you still have a lot of cold air aloft too. And so you've got this perfect scenario where you can create these massive hailstones. So it's it's no joke. Yeah. That's what her back looked like. Pelted. Isn't that crazy? Look at that. Wild, huh? Yeah. So that's what hail can do. It's pretty nasty. Let's see that. That's really sad. Yeah, I just want you to see what it looks like when it starts to fall, because it'll really go. Yeah, you see it? So I mean, look, it's just like ping pong balls. And so, yeah, this is part of the problem, is that sometimes when people out there, if they're, storm chasing or whatnot, you can get caught in the downdraft to where all this hail is. And the problem with that is that if it gets too big or it gets to the size where it's going to start popping through the windshield, you're stuck. There's been a lot. I know a couple of storm chasers that have been out on big tornadoes before, and they get caught in a hailstorm, and it just tears their car up, like right through the windshield, blows out the back window, and then now you're kind of stuck. So, yeah. But see, this is all what, 30 seconds, 45. Notice it's picking up with some intensity too, right?
Mm.
Yeah. So that is.
So if you're out running,
I wouldn't recommend it.
We'd be in trouble.
Yeah, you'd be in
We'd
trouble.
run faster.
Yeah, either run faster or find a tree,
Oh my God.
some kind of shelter. Because, I mean, look at it pick up. And here comes the rain. So notice you not only got hail, but now you got rain. And of course, the wind's going sideways. So, and look how, you see how fast those are kind of bouncing off of the ground. It's because they're all probably coming in at 100 miles an hour, something like that. Not wild? Yeah, that's not what you want to be caught in. Kudos to this dude for standing out there and had his camera when, or had his phone when it started. But, yeah. No, thank you. That is not something I want to be stuck in. So, anyway, so that's hail. So as I said, freezing rain. The way this works is you got these super cooled rain droplets that at least partially freeze when they come in contact with a cold surface, and it creates this little glaze on exposed surfaces. That's why if you see the when you're driving and you see the signs that say bridges in elevated areas may freeze before the road, that's why, because the road is on the ground, and so there's even a little bit of heat from the ground itself, but the bridge is up top. And there's nothing underneath the bridge. It's just wide open. And so that cold air can get underneath and it'll freeze that surface like that. Okay, not worried about acid rain. Okay. So how do we find all this stuff? Well, as you guys found out, and we talked about in the exam, you got to use a radar. The radar stands for radio detection and ranging. Radar. What we use in particular is called a Doppler radar. The Doppler radar basically sends out an electric pulse. It heads towards some kind of a target, hits that target, and then scoots back to the radar. And it tells us, hey, I found something out here. Now what we've done, not me personally, but what the National Weather Service and what the NOAA folks have done is they have created a network of all of these detection systems. And so they continually scan the environment. So basically the radar works is that it goes in a circle, okay? And it just shoots out beams as it goes into the circle. And it starts to scan vertically. So the radar will start off here, and then it'll scan a half a degree up, and then a half a degree up, and a half a degree up, like this, and then go back. So it's kind of like a fan. You know, one of those little sprinklers. Starts here, goes back down, and it just gives you this little vertical slice of what's happening out in the atmosphere as it goes round and round and round. So it monitors rainfall rates, cumulative rainfall totals, how much intensity are we seeing in a shower, a thunderstorm, and a cloud. And it does it by two ways. It either does it by reflectivity, which means that it detects an area of precipitation and it reflects it back to the radar, or it does it in a velocity mode, which it detects air motions either moving towards or away from the radar. Okay? So what are the two? So reflectivity mode, velocity mode. These are two different ways that we use our radar to try to figure things out. So this is kind of what it looks like. So it emits short pulses of microwave energy. They get scattered by rain, snow, hail, buildings, birds, bats, people, anything. And so it sends out a pulse. The echo comes back, and it gets detected by the dish. And then how the computer works is we set it so that it, within a certain range of reflectivity, of the amount of impulse coming back, will indicate to us what type and, more importantly, what intensity of precipitation we may be dealing with as we're out there. Now, what's happened sometimes with radars, and I've been asked this question, the radar that we use here across the greater Houston area is located down in League City, in Dickinson in particular. Why wouldn't you put it here in Houston? Why wouldn't it be most important to put it right here downtown? Why would I want it all the way out in Dickinson, not right here? What would be a problem? The radar sending out a beam, and it hits something, detects it, and comes back and says, I found something. Why would I not want it downtown?
Building.
Buildings. Right. Exactly. And it would be too close. Yeah, there's too much happening. So you have to have a radar out in a fairly wide open area. That's why most of the radars across the country are out at like regional airports, because it's wide open space. There's not a lot of buildings around, because otherwise if you did that, you would just get a signal back and it would just be this big globby mess. You wouldn't really be able to detect, oh, is that a building? Is that rain? I don't really know. Mountains it'll run into sometimes. So you always have to be cautious about that.
All right, so this is what it looks like. Pretty little dome. Looks like a big egg sitting up top. And this is kind of the detection that you'll see. So the radar site is this black dot, because obviously it's a radar, it can't go straight up. So there's always a little hole around it.
And so it sends out a beam, detects what's happening there, goes back to the radar, and then all of this gets computated by the computer to figure out what's the intensity
Based on the color. So the more intense the product is that it's hitting, the brighter the color will be.
Okay, so now velocity products, the way this works is this is all based on movement. So not necessarily intensity of a substance that it's hitting, but it's what direction is the air, the wind moving. It's kind of cool that it can actually not only detect a type of precip or the intensity of some kind of substance in a cloud that's there, but it can also detect a movement and speed. This is used for trying to detect any kind of spin in the atmosphere, or some kind of spin in a thunderstorm, bless you. So like a tornado, for example, okay? So the way this works is that your greens are your inbound winds, your reds are your outbound winds, okay? So in this scenario, what we've got here is we have winds moving away from the radar, and we have winds moving towards the radar. So it's creating what's called wind shear. A wind shear is just a crisscrossing of the winds. Well, if we do that, if I have tight enough spot where I've got one wind moving that way, I got one wind moving this way, it's going to create a little bit of spin between those 2 points, right? So if I, like I said last time, if I have this and I pull it that way, it's going to spin it that way. If I pull it that way, it's going to spin it that way. So I'm creating this sort of like horizontal spin. And that's what we look for whenever we see these signatures. We had a tornado warning a couple days ago. It caught me off guard. I don't remember what day it was. Saturday maybe? Anyway, very weak one, but it was out there. I don't think it ever touched down, but I flipped our radar over to the velocity product and saw this, this is called a couplet, where you get these little red and greens that are real tight, close to each other, like this little scenario right in the center. And so that couplet had an indication that, hey, there may be some spin to the atmosphere, and that's why the National Weather Service put a tornado warning out on it. So the cool thing is, a couple years ago, all of the radar systems across the country got upgraded to what are called 88Ds. 88D, basically, think of it as sort of the high definition of weather radars. Okay? Just like our new satellite that we were just looking at, that picture, that's the brand new satellite, the new HD satellite they put in space. These are kind of like our HD radar products. So it gives us better information about the precip type, accumulations, any kind of threat identification that we can do with that, and of course, gives us a better picture of the size and intensity of whatever kind of precipitation we're looking at. So very important stuff. that's about it. Yeah, let's do it. Okay, I think that's all I got, guys. All this I'm not going to get into today. So that's what we've got for chapter 7.